Thanks, everyone, for your attention. I want to talk today about how generative AI can help us understand what whales are saying. And we're going to be looking at a few questions that I think are important when we want to understand what they're saying. And we're going to be starting with a very, very basic stuff here in this talk. So we're not making any assumptions about what is meaningful about whales. We're not making any discretizations. We try to be as raw as possible. And so one of the main questions will be, what is meaningful in sperm-whale communication system, and how we approach that question in a system that is as unknown to us or as alien to us as sperm-whale communication system. We want to understand what specific rules govern their communication system, right? That's going to be one of the goals. How things work when you put the codas together or clicks together in a similar way when we are asking ourselves in language how things work when you put words together or sounds together. We're going to be talking a little bit about a couple of further steps once we deal with the first two questions. What design features of human language do sperm whales have? So that's going to be one thing that we're going to be interested as well in this project. And also one thing that is very exciting and we should not forget is that their communication system needs to be learned. How do they learn them? How do they learn it? And how do we model that, right? So the end goal, obviously, is to understand what the meaning and what the form is, right? So the pairing between meaning and form is going to be the end goal. But I think these are a few questions I was thinking about, like, what am I doing in this project? These are the few questions that I think I'm asking myself in the work that we do. So we talked about black boxes today already, right? And one of the things that is super kind of one of the frontiers currently in AI research is interpretability of those black boxes. Like, how can we understand them? And one of the important things is to understand these sperm whale communication system, to leverage AI to understand sperm whales. For that, we will need interpretability. We will need to understand what these models are learning. Because if they're only performing, if they're only translating, we will get the meaning maybe, but we will not understand how their language works. So in order to use AI to decode sperm whales, we will need to understand how AI itself works. Why is AI important? Why is generative AI important? Is because humans are biased, right? We hear things that we're used to. I mean, there's parts of communication systems, sperm whales, that we don't even hear, right? But we can analyze. But we pay attention to things that are important to us as humans, and we want to have AI that is less biased, that's paying attention to stuff that are non-humans, in order to kind of understand what is meaningful in this case. And so what we're going to, in the first part of the talk, I'm going to show how you can leverage interpretability techniques to force AI, or like deep learning model, to give us clues about what is meaningful. So basically, it's not that they're giving us straightforward answers. Using these models, interpreting them to shrink the hypothesis space so that they kind of steer us into what might be meaningful in this communication system. Okay, so first, for a few slides, let's forget about whales and talk about language. Human language is great. We all agree about that. Why is it great? Because we know what it is, right? And we do not know what whale communication is. And so we can play on human language and then test on whales to kind of understand what is meaningful. Okay, so what do humans do when we speak, when we communicate? For spoken language, we have information in our head, right? We form information, and we encode that information into waves, right? And then somebody hears those waves. Okay, so the listener hears those waves and decodes information. Okay, So it's encoding and decoding, right? And we understand extremely well how human language works, right? We've been studying it for like thousands of years. Panini lived hundreds of years before, BCE, and we understand it really well. So so the ground truth exists, right? We know that the word like pit is means something else than spit, because we've added the sound there. We know that the word like pit means something else than bit because we changed one sound from one word to the other. We know that sounds change meaning. The sounds that are called phonemes change meaning. We know that there are morphemes. We know exactly how they work cross-linguistically. We know how to create, create words out of morphemes. We know how to create sentences out of morphemes. And so that's all great. And we have acquisition data and so on. So another reason why language is a great testing ground as well is because speech, especially spoken language, has a wide variety of different, more or less complex processes. In the Chomskyan hierarchy, some speech processes are very simple, some speech processes are very complex, and we can test them. We know what humans can learn, and humans are pretty intelligent. So so we have like an upper bound, a lower bound of what is learnable in humans in spoken language. So we're going to be using this as a testing ground, right? So language as a testing ground for later on when we switch to Wales. The models that I'm using for modeling language learning are GANs. GANs are amazing for all sorts of things. I love GANs, but if you think of so we've seen a lot of transformers, and transformers are great for performance. But if we want to build models that learn more like humans, I think we need to switch to GANs. Why? Because they learn by imitation and kind of imagination, and not necessarily next sequence prediction. And that is great because they're extremely creative. It is the only deep learning architecture, as far as I know, where the model, the architecture that generates data never actually sees the data. Okay, and that is huge, right? So the way the training in GANs work is you have a generator that produces data, that generates, and you have the discriminator that has to distinguish what is real and what is fake. So the generator is trained on tricking another network into thinking that it's producing real data. So and unlike in other architectures like autoencoders, it never accesses data directly. That means that there's no direct connection, and it's not replicating. It's innovating, and that is crucial. And for that precise purpose, GANs need to be quite sophisticated in how they learn their internal representations. And we'll see over and over again, we're showing that on speech, they're learning disentangled, symbolic-like, rule-like representations on highly complex processes, which would fall on the more complex aspect of the Chomskyan hierarchy. And so they're extremely creative. They create new words, we'll see, and they represent what we know is meaningful in language with disentangled discrete representations. The only thing we need is a technique to access those representations, and we have that. So that's good. So this is how they learn. So the generator needs to produce data, needs to produce speech, right? From random noise distribution, right? So it takes some random Z latent space, which is uniformly distributed variables from -1 to 1, and it takes a few codes, okay? It uses those small, tiny vector, basically tiny compared to other architecture. This is like a total dimensionality of this is 100. So it takes 100 numbers and turn them into speech, spoken language. This generated stuff gets sent to the discriminator that needs to evaluate what is real and what is fake, right? And over in time, at the beginning, the generator is super bad. It's producing noise because what else would it do? And the discriminator is great because it's so easy to distinguish noise from speech. But in training, the generator becomes really, really good so that the discriminator doesn't know what is real and what is fake anymore. So, and this model had to basically build the internal representation such that it'll output meaningful speech. It's a speech in a very efficient way. Okay, so that's the classic GAN relationship. This is adversarial training. Okay, so what we add for linguistic modeling is this another network, which needs to communicate with the generator. Okay, so what needs to happen here is the generator takes some code which we consider to be information. Let's for a second consider this to be information, encode it into sound, and then this guy needs to look at the sound and figure out what unique information did this generator have when it was producing this particular sound. Okay, so what needs to happen is encoding needs to happen and decoding needs to happen. Everything else we leave up to GANs. Okay, but the idea is this model needs to look at output and say, okay, this unique code, you had this unique code when you were producing it. Yeah.
Can you just explain it again? So you have basically two different inputs. One is random vectors, another one is the code.
Yes.
The generator uses both to generate.
Yes, it's kind of just you stack them together and send it.
What's the overlap in the information between the two parts of the input?
None. I mean, they're both randomly sampled, but this one has either one hot or a binary code sampling. This is a uniform from -1 to 1.
But they do contain similar information because your two networks are able to do some discriminated stuff.
So this one estimates only the code. It doesn't care about this. But yeah, there might be mutual information, but when we are actually testing, there's little during learning. So this random space encodes other things than the code space.
Would be an analogy to phonemes,
well, actually,
symbols.
Yeah, that's a good question. What happens is the code is analogous to words, and then individual bits are analogous to sublexical structure like phonemes. So the network is able to kind of learn that there are words and that there are also subwords, like the words have S in common or words have P in common, and encode both of these things with this kind of bit encoding and also holistic encoding.
So C1 could be, for example, something like ba, C2
yes.
would be,
and it is. In many cases, it is. Yep.
Exactly. On that line, what I wanted to ask is, would it happen that you have an output of the generator that's the same, but for different codes? So the information is different, but the audio format that comes out of the generator is the same.
Well, so these guys need to be efficient in their communication, and you're pointing to a really good point. Is the network could learn to encode anything about speech using these codes, right? It could encode gender, it could encode speaker identity. That would be informative. It could encode length of utterances. That will also be pretty informative, right? But the most informative thing is to pair each code with unique words, which is great. And that happens over and over and over again. So whenever you feed it speech, it doesn't care as much about speaker identity. It doesn't care about how high your pitch is, whatever. It cares about words. Now we're going to be seeing that it's more complicated than when you're looking at training range distributions, you're not seeing a lot because these models are highly complex. Well, we found the trick to really access what they learn is by taking these codes and setting them to extreme values, like 1500 instead of 100. And that's where you're basically getting categoricity and disentanglement really tangibly.
I have a quick question. So if you're using the word phoneme here, how do you distinguish phoneme from morpheme? Because morphemes are the smallest meaningful units. Does that make a difference here?
Well, so what we're observing that they're encoding sublexical structure. We haven't really got into. They can do both. They can encode phonemes, morphemes and phonemes. But well, so there's a separate study, there's an independent study that was really interesting, just came out on Archive. They use these models to train on English and French nasalization, whereas in English nasalization is not contrastive, so just like extra information. Whether in French, it's really, you have to know whether your vowel is nasalized or not. And the model learned these two things differently, so it can distinguish from allophonic sounds from really contrastive sounds. But yeah, morphemes it can handle both, but it is unclear whether it makes really distinct, really a salient distinction between morpheme and phonemes. We're looking into that, and there are people that believe that phonemes don't exist at all. Yeah.
Yeah, so like sublexical units have like certain probability distributions over that, right? So if you're giving it like a uniform code distribution, this pushes it towards certain things or not, or like.
It's actually quite interesting. That's a great question. So let's say it cares about the proportion of data, and if you have like a bit string of 5 bits, it'll use say 3 bits to encode something that is so 3 divided by 5 to the power 5 to the power of 5. No, so 5 to the power of 2 to the power of 5. Roughly the same proportion would be of that lexical structure in the training data. So it's using all sorts of dependencies like that, which is nice because humans are pretty good at this kind of frequency matching as well. Yeah.
Just last thing from me
about
this. So do I understand correctly that the blue part, you never really see the training data, right? So had it not been for the orange part, it could make up completely arbitrary sounds.
Sorry?
So the blue part, you never see the training data, right? So the generator produces arbitrary things, so it can make up the codes and the sounds, but the orange part is what makes it produce.
Yes, exactly. Yes, that's great. Yes. So that's what we use for training GANs. Why is this cool? Because we know that we have to perceive and produce sounds to learn language, right? Perception loop is a necessary condition for our learning. And remember, so we encode information when we decode it, and we also hear what we've said. There's a feedback loop directly from our mouth to our ear. And so this is a better representation of human learning because we have the production aspect, we have the perception aspect. It's from raw acoustic data, so just raw waveforms. We are not assuming any discretization, but discretization emerges automatically. It's fully unsupervised. And we've even shown that humans and kids have similar developmental stages when they're learning rules or when they're learning phonology. For example, tone 3, tone 3 in Mandarin is difficult to learn for human kids and also for these models, which is a nice. So again, we're seeing that acquisition as well has similar trajectories in these two models. Okay, so I mentioned that we're going to have to do interpretability in order to use AI, generative AI, for understanding sperm whales. We need to understand what the AI is doing. And for that, speech is great as well. Why? Because vision is more complex. Most of the work, is on vision, and vision is super complex. You have like millions of objects and millions of colors, and you can have pictures of galaxies and pictures of armchairs or avocado chairs. But speech is quite simple. It has only a few sounds. It's spoken language is one-dimensional, which is also nice if you do interpretability work, because you are adding dimensions quickly. And if you start with 1, that's better than if you start with 2, because it's easier to imagine things that are lower dimension. Also, we can compare human performance with spoken these AI models but trained on speech better, because these are it's called generative AI, right? And if you think of what we humans do on vision, we only absorb vision. We don't produce vision. We don't have big screens on our heads that. Right. Well, there's a lot of layers that were needed to get there. And you can draw, but it's much more indirect. That I'm accessing your imagination. You can imagine things But like imagine Apple, it's very hard to see for me to see what exactly Apple, what kind of Apple you're imagining. Maybe now with decoding brains, it's going to be easier. But that's, you know, with speech, we're constantly producing speech. We're innovating, and the humans have innate generator, basically. Our articulators are innate generators. So for that purpose as well, spoken language is great for interpretability. Okay, so I'm still trying to convince you that these models are great models of spoken language learning. A couple of things that happen that are really important, kind of promising, gave promising results for when we transfer this to the whales, is they learn, they're very creative, so they can produce new words. We trained the model on 8 words, and it starts producing novel words of English that it never heard before, right?
When
Similar.
you said that, you didn't mean the whales.
No, the models, not yet whales. But it's also producing new codas that it never heard before, and maybe those are, you know, similarly possible codas as these words are possible English words, right? So it produced like something like start, dust, carrot, and it also produces sart. Sart is not a word of English, right? But it could well be word. It's following phonotactic rules of English. So from very limited data, from 8 words, it's learning a lot about English phonotactics and putting things, you know, together. We've also observed over and over again that symbolic-like, rule-like, categorical disentangled representations emerge if you're willing to play with latent space a little bit.
Sorry, could you maybe apply to this language? What do you mean by symbolic, like?
Yeah.
Symbolic or like iconic, and then representation.
Yeah, so that's a really good question, because it also kind of touches on what these models are doing and what we are doing. Spoken language is the only continuous physical aspect of language. Everything else is representation, right? Mental representational units, so to speak. But spoken language is the only tangible physical continuous space. And so what we are doing is we're going from sound, which is just air pressure by fluctuations, to mental representations that carry meaning, that have information, right? And that's what these models need to be trained on as well. So the process is similar, right? So discretization. And rule-like and symbolic, like why am I using the like classifier there? Is because some people on the symbolic side would be angry if I just say symbolic, just to protect myself. But the idea is that we're trying to push for how much symbolic representations emerge in models that are purely, you know, connectionist. So where you have no symbolic representations, and this is about, you know, observing. You just give the network continuous sound and see, okay, will it learn symbols?
So like I see an R and like T's and A's, the regulars and new words, but so start, dust, and carrot happen to be words that are symbolic, like for which I can produce a mental representation in my head. But like, does this learning model then think that like Sart is this object?
Yes, that's a great question. Actually, we believe that it has representations to make it, you know, that it knows that Sart is adding S to dark and changing T, but so the idea is that if you have a binary code, right? Each binary code, it represents a word. This is word 1. This is word 2. This is word, you know, this is word 3. But what happens is these models is that individual bits represent what, you know, what we think, what is called sublexical structures, so sounds or like chunks of sounds. And that's how we think that the model knows. I mean, it has a representation of, you know, this is an S added to something else.
So
yeah, which is going to be important when we do this kind of work on whales. Okay.
Sorry, one more question on the slide. So you're producing a continuous signal here
but we're visualizing these things back in phoneme space or letter space. So how are you judging that the actual thing is SART rather than?
Well, you can pass it through Whisper. You can have phoneticians analyze it. You can just do phonetic analysis. Unfortunately, I don't have a recording. I usually play this, but it's on YouTube, so you can listen to them. You're right. To answer your question in a better way, we trained a network that does not just produce sound, but moves articulators, which then produce sound through our external physical model that we're pausing during training. And there we can say, well, it's moving representations of articulators in a similar way as humans are. We have just at ICAT, the paper at ICAT introduced that. And so that's, gives you more confidence saying, well, that's probably.
But like here in particular, I can actually imagine a couple of ways of making SART right. One of which is that you don't actually pronounce the final T and it just shows up as a shortening of the ah, and another one where you actually SART with aspiration. So which of like
I think it's adding S to dark.
Okay.
Yeah, but let's say I mean S is a part of training data, and so is T. The articulator.
You don't have a T in.
No, ST sequence is not.
Yeah.
But in articulation GAN, we call it articulation GAN, the model is producing even sounds that it never heard before, like coffee, or stuff like that. So it's really innovative in an even better way. It says coffee in a New York accent. So it's also on YouTube, so you can listen to that. Yeah.
So a quick question about the phonotactic rules. So it's obviously should depend on the training set, right? So if your training words are something like ask, task, bask, it's unlikely that will be learn phonotactic.
True. Yeah, I mean, it's but you can force actually stuff that is outside of training distributions. So the way these work is, so the main technique that allows this kind of work we'll see later is to just go generate in the latent space after training with extreme values of a single unit. And that's the and then if one unit represents one rule or one sound and another unit represents second rule or second sound, if you kind of manipulate them together, you're seeing this compositional rule that is happening in real time. And maybe next slide will answer a couple of your questions. So we can test as complex stuff as reduplication with these kind of models, and learning happens. Learning happens there, despite Gary Marcus saying in '99. Well, no neural net can do reduplication, right? And it can do from raw audio encodes something as complex as copying. Why is copying complex? Because if you have Piru, if you copy the first two sounds, the copied material will be P. If you have Maru, if you have copied the first two sounds, the copied part will be Ma. Right, so it's not like simple adding S to English plurals. It's looking at what you have in the base and then reduplicating that. And here, I think I actually have. Secure. So I manipulated only one unit in latent space, which is the code that the network used to learn reduplication. And there's nothing that specifically saying learn reduplication. It just learns reduplication because that's the most informative thing to do. And as you're interpolating, the copied material just disappears from the output. So that's reassuring.
Is it possible to back up to your GAN slide?
Sure.
So is the longer term thing that you're hoping to do, I'm going to drop sperm whale training data down here. I'm going to have a language that I create, my GAN creates, and then I'll know that the language uses pronounceable things for sperm whales.
Yes.
And therefore we could potentially teach the sperm whales our new sperm whale language. We can't learn theirs, but we know that this is pronounceable by them. And we know what it means. So is that the goal?
That's there's a description of my next slide. Okay, so can we leverage this approach, right? It learned a lot of things about human language, learn sounds, learn words, and learns complex processes. Can we leverage that to understand what is meaningful in sperm whales? Okay, so sperm whales also have to do this, right? Probably, right? So they have some information, they decode it into their codas or clicks, and they have to decode it, right? So this is how we're treating this problem. And so that's precisely what we're doing, right? We are training again that learn a lot of stuff about language on whales, and then probing it. What did you learn, right? So it's an fully unsupervised model. It could learn anything. It could learn anything about audio communication system. It's not limited to human vocal tract at all. And so we're training it on codas, right? So the generator needs to learn to imitate codas. This is this aspect, right? This relationship forces the generator to produce whalish instead of human language. And then these two guys need to exchange information, right? It gets some code. It needs to encode that information into codas. Now it's going to be a lot of confusion because code and coda are similar things. And this one needs to figure out, okay, what did you encode in this particular coda? Sorry?
The original code you start with, and the whole.
It's just a binary code.
At the beginning of time.
It's just a binary code.
Encoding.
Nothing.
It picks up what it calls, it decides what it calls.
That's right.
This relationship has two, I mean, this is kind of similar to previous talk, right? But it has like it's a two-level thing. On one hand, over on the top, the discriminator generator again is always generative. So the generator is always being forced to be efficient and this thing, what it does, it generates separation between the two parts, like between the code and the rest, because that's the most efficient way. There's a loss being backpropagated. So if the QNet cannot guess what G used as a code, G gets penalized. So G must be consistent, right? So what happens is separation consistency in the code. So the code starts out as whatever, but over time, whenever the same code appears, it needs to code the same thing. Otherwise, there's a pattern.
So
I'm not asking how. I'm asking more.
So you throw in speech, right? You give network a couple of words, and you throw it a couple of codes. Now it could learn anything, right? Because it hears many speakers and it hears many instances of words.
I guess the meaning of the code, that's what I was.
Okay, so the meaning of the code in speech is on the entire binary code level is words, right? I can show that because I can show that extremely well. Because if I go after training and I set this one to 1500, it'll always give me a single word. Okay, and as I mentioned, the bit level, it's sublexical structure because word like suit and sark are similar, right? So why are we doing this on whales? Because we want to have the same system that learns so well speech to learn whatever is there, meaningful, whatever is informative. No, that doesn't mean that that's actually informative.
So natural thing is to compare what you get out of this with what we can code as well.
Yes.
Okay.
We'll see. That's okay. Well, so the thing is, we are trying to, that's the point. We're trying to, learn something informative. That doesn't mean it'll learn what is actually informative in this, but it's a good candidate. It's a pretty good candidate. So we train a model to imitate whale communication and learn something informative, and then we need to introspect. What did you learn? Okay, so first, the model can learn codas, can generate codas, so that's good. It generates stuff that looks like codas. Hopefully, whales would recognize as one of their own.
The thing on the left doesn't.
The thing of we have some So you're bothered by this? Yeah, it's innovative.
It's Sri Lankan. No, the long pause at the front.
Oh, is it? Okay.
Doesn't know that, but quotas like that do exist somewhere in the
Oh,
world.
okay. Well, that's the thing that we're observing over and over again. It's just like SART is not a word of English, but it could be. It's innovating, it's creating new quotas that are now outside of training distribution, but many of them are, I didn't know this particular is Sri Lankan, but it's innovative. I mean, it's probably over generating to some degree, but it's really cool that we're getting innovative data.
But that's an interesting, like, do you see on the language data, do you see phonemes that are attested in languages other than the language that you're training on?
In the articulate where you're constrained with articulation, yeah. Okay, so this is the main thing where we're trying to figure out what did it learn. And so as I mentioned, during training, the latent space is within -1 and 1. Okay, so it's within -1 and 1, and if you sample these variables like this, these variables have a lot of complex interaction between them. They're very complicated, okay? And so you're basically not seeing anything. You're not seeing any effect. So what makes this work possible is that we're taking single units here and stretching them way outside of training range, which means that a single unit overrides all lower level interactions that are there and tell you, this is what I learned. Okay, so to Shafi's question, so we add causal inference method borrowed from causal inference to test what bits represent in Wales, right? So this is right, we're stretching single bit variables instead of 0 and 0, 0, 15, 0, and we're actually interpolating and observing causal effect that it has on the data. So what's learning? So what we've observed, there are two things that are reassuring that come out of this. One says, we observed that number of clicks. 1 bit encodes number of clicks, which is great, because that's probably pretty informative. I think that's what people thought that it's important. And you see 1 bit is getting disentangled. This is average number of clicks. So bit 1 gets disentangled there as you're increasing values here. Timing between clicks is also very important, which is great because that's what is useful. That's what humans hypothesize. We also observe that things that are not necessarily hypothesized by humans, which is spectral mean. And just as we were writing this paper, this other paper came out on cetacean articulation that suggests that they're controlling their articulations more than we thought. So it's actually not out of the question that spectral, the actual spectral properties are meaningful. One thing we also observed, so these two graphs, regularity or standard deviation of the spectral means is important. So in other words, like, am I keeping the center of gravity constant through the clicks, or am I varying it? So then starting higher and then lowering and so on. So I think that's really promising to look into. And I think it suggests we shouldn't be throwing acoustics away. It might be important information here stored in the acoustic signal. What we also observe in terms of rules is that the model learned on limited data that the more codas the more clicks you have in a coda, the more regular the inter-click timing will be. And it applies that rule on novel and observed data, right? It's innovating, but within rules. So the rule is, it picks up on that rule and is able to extend it to novel unobserved generated data, which is good. And so what this, yeah.
So I might have missed this, but how do you tell apart between overgenerations that are valid and ones that are not valid?
That's a tough, because for languages it's easy. For Wales it's difficult. But it doesn't really matter for the question of like what is meaningful.
Why not? Because I guess isn't that helps you decide what aspects of these calls there are actually intentionally varied
No, we're looking at only into what individual bits are encoding.
So yeah, the majority still, like, we selected the ranges with extreme, obviously extreme modification. So the majority of the output is still recognizable, right? So to get a rank ordering of the effect, while the output is still recognizable, not the majority hallucinated, still get the correct rank ordering, right? So that's why we kind of didn't want to emphasize the size of the effect, just the discovery of is it or not.
Yes, the logical question. For the previous slide with the rules, how do you get this kind of information out of the code? I think I missed.
Maybe what's this is representing basically that no matter how many clicks there are in the code, the standard deviation with decreasing value of this encoding always decreases, right? So it's a consistency test. So this is representing only one of the bits. So for all other bits, this relationship doesn't hold. Right?
I see, but one has both. Oh,
and how do you argue it? And then the next step, so that is how you discover that the relationship exists with regularity. And how do you argue that the number of clicks that regularity is connected is because it codes the same bit. And you had enough space to encode.
I see.
Okay, so one of the ways generative AI can be useful is it gives, like, combining interpretability techniques with these models, unsupervised, raw speech models, give us a way to test what else is meaningful. We just focused on 4 things. You can, discover anything that you want. Like, you can test anything you want, you can think of possibly. Another thing we can test with this is compositionality. We're looking into, is there other interaction between individual bits, which would tell us there is more compositionality in the coded structure or not, but we haven't been able to see a lot of compositionality yet. So that's still interesting, and we need to look into this. Acquisition stages, right? I think one of the most important thing in this project is to understand how this is learned and how the acquisition stages work, right? We humans, we know exactly what is more difficult to learn, what is easier, and all human kids pretty much, many of them undergo very similar steps, and that gives us a lot of clues. I'm going to talk a little bit about that later. And there are other things that we, I think, should try and are looking to try, transformers for modeling longer sequences, interpretability of transformers, audio transformers, and stuff like that. But I think it's important to look at the audio and see, like, these models are telling us or suggesting us. It's not a definite answer, but they're suggesting that the audio carries information, and that might be key, because currently we have only 22 coda types, right? If codas can't be words, if this is a complex communication system, because it's not enough types. So audio might be the key there to getting to the complexity. Okay, so this was the first 2 questions, right? What is meaningful and what the rules are there that we need to answer. And I think there's a lot more that we can leverage AI plus interpretability, generative AI, these generative models to get more data, more information, more results. So what I wanted to just briefly reflect on now, this is more like a reflection from now on, are this kind of 2 high-level questions. What kind of design features do whales have? What kind of features of our human language do whales have? And again, not something that I have a lot of results on, but we're getting there. Like, we need to get to acquisition and how this is learned. Okay, so we know what language is, which I said at the beginning that it's awesome. We also understand it really well. Language has a lot of really cool properties, right? We can lie, we can talk about language itself, right? We can we can be linguists. We can use language to analyze language itself, which is meta language, which is nice. We are very productive. We can talk about things that happened yesterday. We can talk about things that happen in imaginary worlds. We can well, everything in language has structure, more or less, compositional structure and stuff like that, right? So those are all the cool things about language. And what we want to do is, I mean, where we want to use AI as well is we want to test it like what whales have, right? And I mean, we're not going to end that discussion here or even start it, but we're going to be, going over and over through all these properties and see what do whales have, what do they don't have. But where can AI be useful? Is basically generative AI can tell us what is possible in non-human communication, right? So it can tell us, okay, these are the things that can emerge even if you're not a human, right? It's going to be on us to kind of go then and test what whales have, but especially transformers really are pushing the boundaries of what is there that is possible, right? What properties of language can emerge in artificial neural networks? And then maybe those same properties can also emerge in animals if they're really smart. And we think that sperm whales are really smart, right? So I think that there is a crucial case to be made that we need to study animals, human language, and generative AI or machine learning together, right? Because we can learn from each other, and the questions are actually very similar that we're asking in these specific subfields, right? There's a common question in animal research that says, is the animal mind capable of human language? It's just we are smarter, right? With increased power, do animals have everything that we have? Which enable human language, or is there something uniquely human, some operation, some, what Chomsky would say, either merge or some, genetic thing that happened there that enables language? I mean, that's the only question. I'm not giving any answers, but the reason why generative AI, which is part of the title, is important here is because it tells us what, we ask a similar question there as well, which is, do current architectures that we're seeing that show a lot of these emergent properties, are they just not powerful enough? And if you increase power, they'll become humans. There's going to be AGI, or is there something extra added, right? Do they need some extra human stuff, human property, or some extra tweak in architecture that will enable human level performance or not? And so those are the questions in parallel, right? And one of the case studies that we just put on the archive is like, we can go through design properties of language and see, okay, what is possible in current generative AI? What can emerge, right? And one of the holy grails of linguistics is recursion, right? If you look at all the design features of language and go in animals, you'll find most of them in animals, either in linguistically trained animals, where you train animals on speech or whatever, or call animal communication in the wild. Like, there's productivity, there's probably compositionality. I mean, there's like monkeys that have suffixes and stuff like that. Most of the design features are present in animals, not at the same time, not in the same way as language, but the principle is there, except one big kind of disputed property, which is recursion, is one of the few properties that is not found in language, in animals. And what is recursion is embedding of phrases within phrases of the same type, right? You can always make, it's kind of, recursion is the infinity of language, right? So
it's not found. How do you know?
Well, based on my research and my we don't know. Well, maybe we will.
Research on animals?
Well, no, there are people that have looked into this. It's disputed. Maybe do you have a case of recursion in animals?
I have a question. So I have, well, in your previous slide, so you say that basically the two questions are, are animal capable of human language, and are machine capable of human level performance? I think it's wrong to the very formulation of the questions, in my opinion, is wrong, because you can define language basically without relating it to human. You can define artificial intelligence without relating it to human. Human is just one example.
Yes, but we're trying. Well, that's true. But we still think that there's something unique about human language, right? That we're chasing.
There are artificial languages that are as expressive probably as a human language. And
yes, for sure. But there, I mean, we put value in humans, and we want. I mean, I'm a cognitive modeler. I want to understand how it's reasonable to expect that animals have faculty of human. No, you're right. You're right. I agree with that. But I mean, there is, if nothing else, for evolutionary purposes, right? Because yes, there are other languages, other intelligences, but from an evolutionary perspective, our last common ancestor are bonobos and chimpanzees. Well, no, so we stem from the same common ancestor, right? 6 million years ago, probably. And they do not have language the way we have, and that's a significant question, right? And so how did that evolve? Is it just like increased power, right? You're just adding parameters, or is there something else? I mean, there's little biological evidence that there's something else, but maybe there is, and we haven't figured it out yet. And because the question is like, you can get into this higher level questions like, can human-like properties emerge in large models? And if you think that human-like intelligence emerged from chimpanzees to us with no extra tweaks, then you could also think that maybe human-like intelligence will emerge as you're increasing the size of these models.
It could be not human-like, could be some other form
of
language or intelligence that is equally capable. It's just very different.
I agree. Yeah.
I just had a quick comment about recursion. It's a tough one if we can't decode other animals to know if they show recursion.
Yes.
But Sue Savage-Rumbaugh has shown some lovely work, and I actually have a video of it, not with me, but I could bring it, where the bonobos have learned spontaneously without explicit training to comprehend human speech. She worked with symbols, but one of them particularly started picking up human speech. And she shows very nicely that when she's masked and she's not cueing with other visual signs, that they can comprehend recursive types of commands, like go get there's a ball right in front of the animal. Go get the ball that's outside and bring it in. So that's interesting when you give them codes, how they.
I agree. I mean, what they didn't perform on is added level. Like they perform at level 1, which is embedding with N1. They didn't perform at embedding N2, and even if they perform on embedding N1, there might be people who say, well, there's just a semantic soup. There's not really secret. I don't agree with that, but they have somewhat valid counter argument. But I agree. Kanzi is a great case, the history of animals, linguistic animal. Yes.
So for me, one of the things when I try to think about like whale speech and trying not to create this hierarchy is this like minimum viable communication product, right? And we're talking about masking and what can we take out of human language before we lose the purpose. And so do you think recursion may be an outlier in human language because human language has so much embellishment? Like I gotta probably ask that question a lot shorter.
So that's that's a really complex, and recursion isn't. And so the thing about recursion is really complex because do we process? When does our processing stop? Right? You cannot have infinite. Like you can always make a bigger sentence, right? That's why I say recursion is the infinity of language, right? So you can say Mary said that John said that whales have language. You can always say Shane said that Mary said that John said. But at some point you stop processing stuff, right? Also, these are not very natural, and we try to avoid several layers of recursion. But it seems to be kind of the design feature. I mean, it seems to be, and it's not just in sentence embedding, but there's a principle where you can take one phrase and embed it, like putting inside a bigger phrase in a hierarchical structure, and that seems to be a pretty well baked in property of language. And I think you're absolutely right. If you don't know anything about language and animal communication, it'll be very difficult to evaluate whether it has recursion or not, right? But I think it would be great to pay attention to that in whales as we're learning more about it. Seeing if they can have smaller phrases into larger phrases, if they can do this kind of embedding. I think that'll be highly consequential. And incidentally, the reason why we're interested in, why this is also part of how generative AI can help in settling these questions is we've recently tested whether GPT-4 has explicit recursion, and it's performing really well. It's the first model that's performing really well on recursion in many respects, and you can identify it and then add layers in what seems to be infinite number of layers. And this is on archive since yesterday, but this is just an illustration basically of how we can basically test, okay, what can emerge in a model that doesn't have anything human, right? There's nothing human about transformers, but they're just very good at things. And we think that whales are pretty good at some aspects as well. So we might be on the lookout for these cases. And then the last, I'll be finished very soon. But the last thing is, and I don't have much to say here, but it's just like a real hope that we need to get into acquisition, and we need to understand how this is learned and how it's transmitted from and how developmental stages work, because that's going to give us really important clues about kids learn the simplest thing first. They learn syllable ma or ba, and as we're listening to them, I think we're going to be getting a lot of clues from the babies. Okay, so I think a couple of tangible results. We have a framework that tests which properties are meaningful, which is basically combining interpretability with generative models. And we have a tangible result which we shouldn't be throwing acoustics away. So basically, I think the main two ways where generative models can help us is to understand what is meaningful and test what is meaningful. And then to test what is possible in non-human intelligence, so that we might be on the lookout for various properties. Okay, so a couple of the papers, the QR code will take you to the link with all the papers, and thank you for your attention.
On using human language as the benchmark, would this process be able to spot properties that are not found in human language, but could be found in whale language?
Mm-hmm. Yeah, it's as unbiased as, it's still biased and still limited, but it's as unbiased as you could hope for. The question is, will we be able to
see it, to recognize it? Yeah.
To make, use these techniques to extract that information. That's a tougher part.
Yeah.
Thanks. Thank you for the talk. I was wondering, with GANs, you can generate novel utterances, or potentially you could generate utterances that are designed to closely approximate something that actually exists in the whale's communication system, but maybe produce like a different version of the same thing, like, the same word in a different speaker's voice or something like that. But I guess with human language, we have the advantage of being able to say that the output of a GAN sounds right or doesn't. But with the whales, we don't have that option. So what do you think we can do to overcome that obstacle?
Yeah, you can do it.
If we want to do playbacks in the future, for example, how would you design the model to generate whale vocalizations that are meaningful without knowing what is meaningful?
So this actually relates to the question Pratyusha asked, right? The way the methodology works, we're testing for what it considered, like what it is decided to encode from this interaction with the data via the discriminator, right? So that's like one check. And I don't know if it was extremely obvious from the plots, we were actually varying the encoding, right? So along that variation, each point represents like thousands of examples, right? So not all of those were spurious, right? So it's more of a question, I guess, than it decided to encode this, and using this rule, it generates new stuff, right? And the fact that it uses this rule to generate stuff that's not seen is the answer itself. I don't know if I can.
Well, I guess the question is like, I'm thinking in terms of potentially doing a playback experiment. If you want to do a playback experiment of the whales, you have to know not just that this is something that is probably meaningful to whales, but you have to know what it means. So if you have a model that say, I don't know, like, let's say you figure out that this particular call means let's dive now, right? Just as a simplistic example. And then you want to generate a version of that call in the voice of a different whale saying, let's dive now. You have to know not only that it's a possible call in the whale's language, you have to know that it means that specific thing.
Well, we don't have external meaning yet, so this is all internal meaning. But the fact that I think one reassuring fact is also, yes, GANs can always be, can always overgenerate. But one reassuring fact is that we found two things that are, human style very meaningful, are very prominently encoded as meaningful as well there as well. But so this is, none of this is yet, external meaning form pairs. That we don't have that yet.
Right. I was thinking more like as the next step.
But you need to know what to look for in the next step, right? That's hypothesis shrinking part, right? Because it's gonna make our life much easier if we know that acoustics should not be thrown away, for example,
right?
And stuff like that, right? So, but yeah, there is no external meaning yet. Just like there is no external meaning in words, but words have meaning, right? So it's possible that the things that the whales are learning actually, has external meaning. It's probably even likely that it has external meaning. We just didn't make that connection yet.
Right.
Yes, I see how you would do it without testing on the whale side, because they're the only animals that actually know what anything means.
Yeah, of course. But the challenge is you can't just do infinite playbacks.
Yeah, so that's the biggest challenge. That so we were able to get around the problem of experimentation here, just to decompose like building blocks of the communication, because we could simulate it via a GAN experiment, right? But unfortunately, I don't think we have training data to be able to train a simulator, which we would input our reconstructed utterance from these building blocks, and the generator would be faithfully give us back what the whale would do, because that's almost impossible to do.
Right.
Yeah.
All right, thank you. Really appreciate that. So we're now going to break for an hour and 25 minutes for lunch. And yesterday, Shafi brought us to the law school, which is just nearby. So lunch is on your own, and we'll see you back here at 2:30.